My name is Paweł Sosnowski, and I will have the pleasure of being your host today and show you this new way of making your engineering and simulation combined together. A short agenda. We'll start with the introduction to computer-aided engineering. Afterwards, we'll have a word about the SimScale approach and what is it that we're doing. I'm aware that most of you come here because you had been working with Onshape so far. We have the designs done, and you're working with the tool quite a lot. Then I would like to add additional level to the work. Further, we'll go with the project. The best way to learn is to have an example and see how do we do that. And afterwards, when we have the process done and seen on our own eyes, we'll talk a little bit about the benefits and move to the Q&A session. All right, I immediately see a request. There's a request to turn the volume up. I might get my mic a little closer, but I would highly recommend you to check your output, your speakers, if you're catching them. In general, I had a very good feedback, and so if any of you have the same problem, do raise your hand now. We'll try to fix it before we go, or just please check your speakers and make sure that they are set as that's good. Oh, I see another feedback that everything is fine. So I guess this is just a local problem. All right, let's move on and have a short introduction to the computer-aided engineering and why is it that we are willing to do that. Before we move on, we have to think, what is the development process of any kind of a product? We start with a design, usually a CAD, and right now the possibility of making it in Onshape makes it super easy to develop and run. But after we have the design, we are bound to make a physical prototype and test it in order to check if what we made inside a computer is really working. After the testing, in most situations, there will be a redesign phase, some kind of modifications. And this kind of a loop where we go back to the redesign part and change the CAD itself happens several times before we're ready to ship our product. Obviously, if we're dealing with a small part, like a screw or a small electronic board, everything is good. It doesn't matter if we make 100 of them before we reach the final ship-ready product. But if you're talking about a big construction, piece of an engine, ship component, it is not really possible to make a test. Well, we still make a scale test, but not a real full-scale test. And every part of this iteration is quite costly and time-consuming. What we do is we take the computer-aided engineering approach, where between the physical prototype and the design, we put a sub-loop of the simulation. And with the results, we're ready to perform an engineering decision before we make the first prototype. Obviously, this loop can take several times, as it did, and it does not eliminate the requirement of building the prototype itself. At the same time, it reduces the amount of prototypes we're required to make and makes the whole process much safer, especially for big engineering projects, and also cost efficient for smaller ones. What is the SimScale approach? First thing to understand is the on-premise tools that are available right now. In general, they're quite cost-intensive. Let's not fool ourselves. It's not so easy to learn them, and there are extra maintenance and deployment efforts that are required, which brings the three barriers that prevent most of the engineers from using these awesome tools that the simulations provide: the financial, technical, and know-how barriers. At SimScale, we're trying to combat all those barriers and go ahead of them, providing an efficient, cost-effective, and tool that is available for everyone. All right, that was hopefully, I made a short introduction because I know that you're all here to see the project and how to do it yourself. So, as I mentioned, let's define it. And the best way to do that is to have a real, or not real life, but an example that resembles life. Let's imagine a situation where our business partner provided us with a piece of electronics and asked us, hey, I need a box to enclose this little thing. It will be mounted on a machine that will be vibrating, and the environment will be pretty dirty, so you need to make it enclosed. Well, we take the challenge and, of course, start with the CAD. That's where Onshape comes into place. And just to make sure that we are all seeing what I'm seeing, in this particular case, I created a small project and designed the the PCB board myself. A little bit of playing. Obviously, I'm sure that most of you are very familiar with the ways Onshape works and the possibilities of having these designs done in a very friendly way, a little different from the standard CAD tools, but I will not be talking about so much about the design since I'm not the expert, I'm the simulation guy. At the same time, it was very easy also for me as a beginner to perform and make a pretty nice representation of a PCB board. Now, the job would be to start working with the design of our box. Obviously, we start with a part studio where we already see an example in the whole glory, at least the first thing. Again, we'll take a benefit of Onshape's possibility of hiding intermediate steps before we arrive to the final stage, where the first thing will be to have a derived path from the PCB board, which contains the biggest elements present in the system. Afterwards, I'll just begin with a sketch. Have it extruded a little bit up to have the thickness of the board established. Extrude the walls. I mean, right now they are not showing very well, but after I give them some thickness, we see what happens and we have the walls ready. I decided not to close my box, but first create a sketch on the top that would represent and have the representation of all the holes and ventilation system that should be present in our PCB board. There it is. And of course, the next step would be just to make an extrusion of the face. At this point, there's one thing missing that should be added, maybe a little earlier, but I just forgot. We need to have a specific faces that will define the mounting points of our box. That's why I would create a sketch on the bottom face and perform a split of the face using the sketch itself so that we have separate faces 1, 2, 3, and 4, which will mount our box to the element. All right. We made our first design, and now it's time to make the first tests. We could build it, or we could go and perform the simulation. The first thing would be to decide on what kind of types of simulations are we looking for. The first and the simplest one, especially for vibrating systems, is the frequency analysis, where we will be looking for eigenmodes or the normal modes of vibrations for the system. I see that right now, just for a second, I'll stop. I see several hands risen. Please post your question in the questions section so that I can address it if possible. If everything is okay, I'll allow myself just to drop the hands down. All right. Let's move on with the eigenfrequencies and eigenmodes. I like to think of them as the particular frequencies at which resonance would occur in the system. In the end, the great thing about them is that they represent the fundamental deformations of the structure. And any kind of vibration of this system can be represented as an interpolation of eigenmodes with a specific participation factor. And of course, what is interesting for us is at which frequencies will we have deformation and how will it look like? At the same time, the frequency analysis has one weakness. It provides us only with the general shape, not the real deformation that would happen at a particular vibration exciting system. So the result can be scaled arbitrarily, and it may look terrifying, but in the end, the real deformation is just a micron. For this, in order to address the real deformation and the real values that are happening, we perform the second analysis, the harmonic analysis, which will give us the steady state behavior of a system as if it was undergoing the vibration for a very long time. We're just looking at the steady state part of a particular frequency, and we're making a list of simulations that will check how does the system behave at them. All right, we defined our job. We know what we're trying to do. Let's prepare the simulation itself. I'll jump right now to the SimScale account. Well, first to the web page. We just sign up. And the first thing we'll notice is a dashboard, which gives an overview of all the projects that we were working on. I already have a PCB system analysis ready over here, but for the moment, I'll create a new project just to demonstrate how easy it is to upload the geometry from Onshape to SimScale. Of course, we'll need to give a title, test upload. We'll give a certain description, test description. And now there is one thing that you also will notice. There's a checker between public and private projects. An awesome thing is that you can perform any amount of simulations for free and share it with the community. This will allow you to extend your knowledge and get the benefit of other engineers helping you work on the project that you want to do. Then there is a possibility of going professional and work with private projects. All right, let's jump and create one. This time it's an empty project. I'll just jump to the dashboard of this little thing. Obviously, no visualization, no views, no likes, nothing happened so far. And I will open it and go to the workbench itself. In general, if we had a geometry, a step, or an IGS or a BREP, STL, you can simply upload it and have your simulation start at this point. But then we have a very smart integration with Onshape. You just click import and choose import from Onshape. As soon as this will happen, this little application will ask you for permission to access your Onshape account. And as soon as you give the permission, you will have the overview of the projects that you were working with so far. Let's go to the PCB optimization. And here we have the objects that are present in our drawing on Onshape. Just to take a look, all the elements that are here are present. And, oh, sorry, not this window, are present here and ready to be chosen. So I can go and choose the box itself, get particular parts, or the full assembly itself. Well, this is, I think, the box. So we'll have the whole assembly ready. Click import. And after a few seconds, we will have it uploaded and ready to perform the simulation itself. Now, what are the steps that we need to make in order to get our numerical investigation of the problem? First is the pre-processing. We'll discretize the CAD geometry into a mesh, a discrete representation of the project. The meshing on SimScale is done in a very simple way. You just mesh the geometry and choose one of the meshes that is available over here. We have always a manual mode, which gives you access to quite a lot of parameters, or an automatic mode, where you just select how fine you want the mesh to be. I'll just keep the automatic one. Obviously, we'll not be running it because it takes a second or a few minutes, depending on the fineness of the mesh that we want to have. And in order to get and see the results themselves, I'll just jump to the project that I prepared earlier. We'll take a look at it. A short overview, very easy. Let's open the project itself. I have multiple geometries already uploaded. That is, as over here, we have other boxes. There is a question, is the mid-surface meshing available? You mean a surface that is within the geometry itself? In general, you should provide a geometry or a solid element that is whole within itself. If you have surfaces inside, they will be considered as obstacles for the mesher itself. Or you can have the part made of several elements that later will be bonded with specific contacts. All right, so the first attempt I made in order to create this mesh was just to go with a parametric tetrahedrization and split the domain into triangles. And I was not very happy with the result, so I made a little finer mesh. This is obviously the first approach. Anytime we're loading this kind of object, it requires a little bit of time since the renderer needs to work for a second. Let's have a representation of the surface. Surface with edges, pretty fine mesh. It's always good to have at least one or two cells present on any surface that we're trying to simulate. So in this particular case, it is just a thing. And we can take a look after I hide this little surface. On the insides, all the elements are also meshed with a very nice thing. Okay, let's prepare our first simulation. This will be simulation number 10. Whoa, I made quite a lot of them. All right, there's a clarification of the question that we had. Is the option available to generate the mid-surface from the solid? After that, the mesh is generated from the surface. In general, what is happening within the mesher itself is that we will have the mesh created first on the surface itself, or first on the edges of our geometry. Every edge that is present over here will be split with certain fineness, and later we'll start creating surface meshes and surface discretization of the geometry. After that, when we have the first surface mesh, it will be growing tetrahedrons, or basically triangles, prisms. It can also grow prisms, it can grow triangles, it can grow basically tetrahedrals. So we have, this is growing inside, and then there are refinements that will remove some cells, make more of them, and so on. Oh, and there is another question, do we support shell elements? And this is, I think, also refers to the same question. Right now, the shell elements are not present yet. Pretty soon, we are planning to release this feature, and it will be available to the simulation community and for everybody to work with. All right, but first thing will be to, let's go back to the analysis type and choose what do we want to do. Anytime you go here, you have access to all the possible simulation types. In this particular case, we are looking for the frequency analysis. And as I click Save, two things will happen. First of all data will be stored, as in the case of Onshape, on the computer service. We can have a lightning struck our computer, all the work is preserved. Second thing, which you might have noticed, is the appearance of the tree on the left side in the simulation tree panel. Right now, we have a template for our simulation to work with, and the job will be to make a simple top-down approach, entering every node and every leaf of this tree so that we can prepare the simulation itself. Choose the domain, choose the materials. Oh, of course, it has to load a little bit. Now I will add 2 materials. The bigger the mesh, the longer it may take to load the path, and in this case, it's pretty fine. We can choose the material from the library and assign it to particular elements that we are interested in. I made some choices earlier. After that, there's the possibility of choosing the constraints, preloads, selecting the solvers, choosing the amount of core hours, the amount of cores, and most importantly, allowing to run the simulation on a supercomputer. In this particular case, you have the choice of going from 1 to 32 cores that will be performing the calculation. And even better, you can have any number of simulations running at the same time, because all of this is going in the background. While I set a simulation and make it run, I can go out from SimScale and work on my CAD design back on Onshape. Even more, I can have 3 different designs being calculated simultaneously and provide me with interesting engineering results. Okay. Let's take a look at the results themselves. So once more, I will just jump to the first simulation that I did. In this particular case, I will not go through all the settings. What was required and important was setting up the contacts in order to connect all the paths together so that they hold, setting up the material properties, and basically choosing the number of computing cores. For model, there is a very interesting question. Could I recommend the number of cores to use? Does more cores allow us to get faster the results, or does it cost more? Obviously, there is a limit on the amount of core hours that you have. Every user has 3,000 core hours available at his disposal for the time being. Of course, if you go close to the limit, you can just contact us and we'll see what we can do. But obviously, getting more cores will increase your burn rate. Every real life hour of running on 4 computational cores will burn 4 times more computational power. At the same time, you get the speed up of the simulation. What I like to think about whenever I do select the amount of core hours is how big is the project. For smaller ones, it doesn't make sense to go with the maximum computational power. It would be as if we had people trying to dig a hole. If you put 32 workers to dig a small hole, instead of doing their job, they will be talking to each other. And that's exactly what's happening with the processors. They will be exchanging information instead of doing the calculation, and they will be waiting for the laziest guy or the one who has the most workload. In fact, so the smaller the case, you can run it on smaller jobs. For model analysis, the only limitation is the memory itself. And anyhow, the calculations will be performed on a single core because it's really, really fast. Okay, I'm glad, I hope that this explains the issue. In this particular case, we were running on a very big mesh. It's a relative, well, not a extremely big, but pretty big mesh, and it took 24 minutes to perform the calculations. So we have the simulation done and we're ready to post-process them, you can also do it online using the online post-processor. We have another question. What is the name of the solver performing the calculations in the background? And are the hex elements supported? Right now, well, the solver can be seen inside the simulation setup. I'll just jump after we load the post-processing window. Hex elements are supported, but unfortunately the measures that are here are not providing you the possibility to mesh for structural analysis. You can use hex elements for fluid dynamics. At the same time, you can upload your mesh that will be that will be created of hex elements. We are using the solver that's been used for this particular analysis was CodeAster, and the eigenvalue solver was RPAC. This is the only one that is available here. In order to check what kind of solvers are available, you just go to the analysis type and choose the solver perspective. Right now, we're supporting OpenFOAM for fluid flow analysis, Calculix and CodeAster for structural analysis. I personally prefer to work with CodeAster since it's much more powerful, and well, the French build nuclear reactors using it. SU square or SU2 is used for compressible simulations, and JADE or JADE for particle analysis. Okay, and there is one more question regarding the core hours. Are they, the limit is for the free community account, you have 3,000 core hours per year. And in case you get close to the limit, just talk with us. We might find something. Okay, so we have the visualization ready. Let's warp this thing by vector. And I remember that the first thing, let's make the scaling factor 0. Remember that any kind of eigenmode or frequency analysis and any eigenmode has an arbitrary scaling. So what we'll see here is some very ugly blob, but all we need to do is make a proper refinement or proper scaling of the result, which is pretty easy. I just remember that we just go 100 times down. Oh, even less. And this will provide us with the possibility of visualizing our result without downloading them. Everything is done in your web browser directly. So let's have, there we go. And we could color this with the displacement, which was the only available field right now. I took the liberty of making the post-processing a little earlier so we wouldn't have to wait for all the data to load. And these are the results that we obtained. Take a look at the first eigenmodes, which happen at 186 Hertz. And our design has a little flaw. The separators for the ventilation system start to vibrate. Another thing that we observe is that at 195 Hertz, the PCB board starts to deform. In this case, we can gain credibility with our customer or our business partner and say, hey, look, if you put your PCB board in this configuration to your machine, it may start bending. It might break. So we propose either to add additional mounting if he agrees on, or he should change the design. At the same time, we still observe that up to 300 Hertz or 270 Hertz, there's quite a lot of things happening with our separators. A simple, fast analysis gave us understanding that, well, we need to do something with the connectors. The second result is the harmonic analysis, where we can obtain the real stresses that are acting on the board and on the elements, plus the displacements and the modules, which are the physical result. And I'll just jump step by step through the frequencies. At 185, we're reaching the first eigenfrequency. Obviously, if I would hit the frequency exactly, we would have an incredible deformation. That is the resonance that would be happening. At 190, we're getting close to the second eigenfrequency, which will blow up in this particular scaling of the deformation. I just scaled it, toned it a little down. This is the same frequency with a proper scaling, so it just visualizes what's happening. And we can go further, see the other deformations, and another, this 235, we're getting close to the further eigenfrequency that is present for our system. All right. We have our first analysis done. Oh, I skipped the further frequencies. You can see the deformations that are happening, and obviously most of it may regard the PCB board itself. Some of it still happens on our box, which we are responsible for designing. So we had the look at the harmonic design results. Let's go back to our CAD and make a modification based on the observations we had so far. Now I just have to select the proper window, which obviously is not always easy. So we had the assembly itself, which was earlier done. Now we just make a copy of our part studio, box V1.0, and perform modifications. You already see what I've done, and I'm sure that you already anticipated the little change that I decided to do. With Onshape is as easy as adding a sketch to my design. Let's make it look more or less similar. So playing a little bit with fillets, playing a little bit with some lines, and simply extruding it back to create a new part, which will later be used in an assembly. For this particular one, I imported the PCB board just to have the whole thing ready, and added the box from the new part studio, created two mate connectors, similar way to what I did in the previous job, and fastened the thing together to have a nice proper relative position of both of them with a small offset, well, which resembles the real situation as we want it. Okay, and what do? After we have the part, a new assembly ready, we jump to SimScale. We go back to the mesh creator and import from Onshape the new design. Fast, simple, and everything done in a web browser. So let's just check the thing to happen. We have box 1.1 importing, and after a second we will have it on the simulation tool ready to be meshed. Obviously I already did that, so we are just waiting for the thing to get transferred. Ready. There is box 1.1. We can rename it, save, everything is done. Right now, we can use the same parameters that we used for creation of the first box. We had nice mesh, so why not duplicate the whole simulation? So duplicate the mesh. I'm jumping ahead. There's the duplicate at the very end. All we have to do is give a new name, new test, and change the base from the first mesh to the newly uploaded thing. Oh, it just had to load for once. Obviously, when you change the base for the mesh, you will lose the results. That's why anytime I do this kind of modifications, I make a duplicate of the mesh itself. And there are no mesh refinements provided. All I have to do is click Start and wait for the job to finish. Obviously, we'll not be waiting. Just take a look at the mesh that was done in advance, while the little thing will be calculating in the background. And at this moment, the demo account does not have the meshes, any meshes being calculated. Oh, sorry, I'm just clicking randomly. But we can have any number of operations running at the same time, any number of jobs, all of them at once, grinding the numbers and providing us with required data. So with the mesh ready, we're about to go and create the new simulation. In this time, there's a little bit more work than creating a new mesh. Obviously, we can go for the model analysis. Number one, duplicate it, and once more switch the mesh. But as soon as we make the switch, once more, we will remove all the connections that we made, all the contacts, all the assignments of materials, which will have to be done once more. But definitely it's much faster than setting up all the parameters by yourself. Okay, so at this moment, you notice that some of the leaves in our simulation tree became red. This means that they require our attention and there are missing assignments. I'll just rename our simulation to keep consistency and know what's going on. And earlier, also, I took the liberty of grouping the faces. Most of them, by default, have a pretty bad names. So you can just group them, select several. Let's say I will select several of the faces. I'll create a new set, group of faces. And some of them are already assigned to other groups, so we get the warning. I created a set of the ABS plastic. I created the set of quartz elements. This will be required for the material assignments, some aluminum elements, and some resistors. Let's hide this little guy here. Some aluminum elements, and then several faces, such as connections. Oh, this one is not showing because I just hit the box. But this is the connection of the power supply to the box. We will have some box to PCB. Obviously, there is nothing because the box is hidden. We have the PCB to box, PCB to electronics. Quite a lot of little faces. Let's do the following. Let's hide this little guy, this little guy. And obviously we have to decide the electronics parts to be somehow connected. So we select the faces and later will be attached to the board. After having the grouping done, I just go, this is box to PCB, we'll keep it consistent. Master face, box to, oh, which one is it? Box to PCB. So we start with box to PCB and PCB to box. When you have the grouping done, it takes you 2 minutes to set up the whole thing. I have another question. Can you also simply simulate product inaccuracy? For example, I have two parts that are composed of one to another, and together with the turns, and I want to specify the tolerance with which they can be made to avoid excessive vibrations. Yes, you could do this kind of simulation. You could have, let's say, well, we would have to have a representation of this two parts very close to each other. You could define a particular type of contact that would disallow the thing to move. But in this case, it would be you could perform the harmonic analysis and visualize when the parts are overlapping. Or there is the advanced dynamic analysis, which I will not be covering today because, well, the time constraints, where you can define the real contacts, physical contacts, and you will also see the stresses that are happening when the parts would hit each other. So there are possibilities of doing this kind of advanced simulations. Obviously, all these settings can be done. We're just preparing the thing real quick, assigning the groups, choosing the constraints, and so on and so forth. And after we're ready, we can make our second simulation, the model analysis. This time it was a little longer, 4 minutes. We have more nodes. And again, we can visualize the results and see how did we improve. So, oh, I just clicked the wrong thing. This all happens too fast. So let's take a look at our model results. First thing we notice is that the initial eigenmode we find happens at 195 Hertz. And even more, oh my, this shouldn't be showing here. Yes, definitely my phone application should not be happening here. Sorry for that. So the first mode appears at 195 Hertz, and it is not regarding our box. The first eigenmode that would affect our part of the design is at 296. We moved the problem to a higher frequency range just by making a small adjustment to the shape of the geometry. Further, if we take a look at the successive eigenmodes, you will notice that they are mostly happening to the board itself. In fact, the next mode that would involve our box happens at 500 Hertz or 507 Hertz. That's a pretty good result. And if we take a look at the harmonic response of the system, we will do the same analysis from 170 Hertz up to 250. So these are the first deformations that are happening. Obviously, when we are getting close to the eigenmode of the system, it goes crazy. So let's scale it down, at least scale down the deformation, and jump forward to see how does the system behave. And close to 250, we have the very small deformation happening to our box with relatively small stresses. That's a very good sign. We improved the design. Okay, so these were the harmonic results, version 2, the updated box geometry. So what did we get? Within 24 minutes of a frequency analysis, we were able to see the basic deformation and identify at which vibration frequency the problem may occur. We can tune down the engine or perform some kind of optimization of the shape itself in order to get rid of the problem. Further, we got the credibility in the eyes of our partner, to whom we say, hey, modify also your PCB board. All done with the benefit of working online. I will not spend too much time on the benefits of like discussing all the possibilities. We're all engineers here, and I'm sure you're eager to ask several questions at the end of this session. So I'll just direct you to our page, simscale.com, where you can study it yourselves. And I'll give you a little something about the upcoming sessions. Today, we had a short glimpse at a very small fragment of structural mechanics and finite element analysis in representation of model and frequency analysis. There's more possible. Next session, we'll address a little bit of thermodynamics when we'll see how does the PCB board heat up. And for the third session, we will talk a little bit about fluid dynamics and buoyancy simulations, buoyant flow, with combination of using the thermal results from the structural analysis to the fluid. There's another, all right, so this was, let's say, the thing. We're ready to jump to the Q&A session, and I'm happy to see some questions appearing. Just let's start shooting. The first one, can we model physical damping units such as isolator mounts in our PCB example? You can add damping as elements for particular bodies or particular elements. In fact, for these simulations, let me just show you right away. It is a part of a material property and is available obviously for harmonic simulations, since with the model analysis, we're just looking for eigenmodes. So over here, we jump and you can choose the type of damping you would like to have for a particular material. In this case, I gave 0.05 of hysteric damping. There is another, the Rayleigh damping also possible if you so prefer, or you can simply switch it off and remove any kind of this particular physical property. In this particular case, the damping that was included in the quartz elements that are just these two little boxes obviously did not influence the results. Or we could imagine that we could have some extra elements on these legs that would have much more damping, some kind of, as you suggested, some isolator mounts in order to remove excessive vibrations for the thing. So yes, definitely we can do that. All right. Any more questions? Well, there's not much going on so far. If you have more questions, just raise your hands and I'll be happy to start typing. Another question is, are the composites supported? At the moment, the composites themselves are not yet there. We're working on including more advanced materials also for the purpose of modelizations, but then there are several advanced non-linear materials available. So let's just jump to the example of advanced static analysis. It's CodaSter with non-linearities available. And for the materials themselves, as soon as I add an example, we are supporting linear elastic materials, plastic materials, and hyperelastic materials. Then you have a free reign of choosing the parameters that are required for the model that you choose, for example, for hyperelasticity or plasticity. I know that this might be a little overwhelming when it comes to the amount of possibilities, and I myself was pretty amazed what can be done. In this particular moment, I would highly encourage you to sign up and first of all, check the first steps that are available under help. Then there are several tutorials present videos that will show you how to go through the simulations. The great help comes from the documentation, where you can find a lot of description about each and every model, also with practical examples of how to set things up. Last but not least, we have the forum. The awesome SimScale community, people who are willing to spend their time and work together, talk about simulations and work with you to get the results going. And if this is too little for you to start, let's go back to the SimScale platform. Oh my, obviously the forum. Let's jump to the platform. And let's go and see the public projects. This all things here, every project here is available at your disposal. It's a great place to start whenever you're doing any kind of simulation. Let's say I would like to start some kind of impact analysis. And this is a complex one, going with a poor guy who is he's hitting a wall. What will happen if we have a helmet or not? It's a simulation that you can simply open and select import it to your own account. Let's just have another example. What could be interesting for us today? Obviously, there's quite a lot, so let's just search model analysis. There is some kind of a test for model analysis made by one of my colleagues. So what I can do is simply make a copy. Obviously, for free community users, you will have a public copy. And again, this is a copy of somebody's project. It appears in our library, in our dashboard, and we can make modifications to it, play around, and improve the design. Talk together on the forum about the topics, comment on projects, like them, and support other people who are working with it. Okay, so once more, public projects, forum, first step tutorials, documentation, and on the main page and on our YouTube channel, you can find quite a lot of elements. Oh, there's another question. If you're not sure if the project would be interesting, you could also first view it and copy it. Of course. You don't have to make a copy itself. We can just go to the dashboard. Oh, sorry. Public projects. Let's say these pliers. Just go here, view it. SimScale takes great care about your privacy and security. So even other people cannot make modifications to your projects. They can only get their own copy and acknowledge you or give you a thumbs up. It's a good thing. So what you can do is have a view of the current state of the project. Furthermore, for professional subscribers, if you have private projects, whenever you share them with other people, they will remain shared, will be shared private, not possible to be viewed by the whole community. I mean, we have intellectual property, that's very important. But obviously, we can just take the benefit of viewing the project and having it as a starting point for our own simulations. See, how did we define the contacts? Well, there we go. The assignment is here. How long did the simulation run last? And even visualize the results. So we're in a viewing mode. And then we take a copy or leave a comment. Great job. Let's just jump to some kind of an example. You can directly leave your comments below. This is a nice description if you like. As easy as that. Well, I'll not bug another colleague of mine. All right. Are there any more questions? I would be happy to answer them. We're getting close to the end of our meeting, so if there are, do raise your hands and please start typing. I still see a few hands risen. Remember that I cannot hear you, so please use the chat option and just type your question. It should be available, well, it is available in your GoToWebinar. Another question, can I import my own mesh? Definitely you can. There is of course, there are certain formats that we are supporting. So let's jump to our test upload case. Take a look at the overview, open the project. So right now we took a look on how to import CAD designs directly from Onshape. You can also upload your CAD designs and geometries from files stored on your computers using STEP, IGS formats, BREP for people who are familiar with Salome, and STL, which I would definitely advise you to go with STEP or IGS, since STL will only carry the information about the surface and it does not group the faces themselves, just the triangularization of the shape. And to answer the question about the meshing, you can upload the mesh itself. We support UNV format, OpenFOAM format, EGC, and MED formats. Obviously, there are works done to extend this. Another thing is, where can we see the security standards for SimScale for private projects and IP concerns? Another very great question, and obviously important thing for anybody who decides to use it. If you go to our product, there is a subsection called security, where you can read all about the security measures. And if, well, this is not that much, obviously you can just contact us directly and our team will be glad to answer any detailed questions regarding the security measures that we're having. From my side, I can tell you that any kind of communication that goes between your computer and the servers that are located in Germany is always secured. All data that is stored on our servers is encrypted with high security measures. Any transfer between our servers and the computational centers that are located in Europe is also encrypted and obviously packed and encrypted. The same data securities, right now the data centers are all located in Europe and undergo highest restrictions when it comes to security measures. So all communications is done this way. Obviously, if you share your private project with somebody, it's like showing your credit card information on the internet. We cannot prevent you from doing that. At the same time, when it comes to data transmissions, it all follows the high standards that are set right now by European Union. Another question is, have simulation results been compared with some standard results? Yes, we try to make sure that to prove that the solvers we're using are accurate. You can go and check all this in the documentation under validation cases. This is the list of validation cases that have been performed so far. We're obviously extending it every day working to have more and more done. All those validations are done on standard cases, articles, and literature available to the public. Another question, will the standard Nastran format be supported? We have this in plan, definitely, to extend the amount of formats that are supported. At the moment, it is not. And what I would suggest is to work with exporting things to STL, STEP format or IGS. And the CAD tools, most of the CAD tools allow this and do a pretty good job. Or, obviously, use Onshape. Come on. All right, I see some more hands risen. So please pose your questions. Another question is it possible to generate movies in SimScale post-processor? At the moment, what you can do is create screenshots and save states. Some of you may have already noticed, oh, I have to select the project. Ah, lovely. Okay, let's jump to some kind of an example project. I'll just choose the one that we were working with. So you might have noticed a little logo and at the edge of the post-processor. That was the ParaView logo. Those of you who were working with OpenFOAM or with open source tools, I'm sure that are familiar with ParaView, which is used as an engine for our post-processor. All the results that you download from SimScale are compatible with ParaView, and over there, with the excessive advanced tools for post-processing, you can do movies and animations. Another question, one of the parts I created in Onshape did not import, but I don't know why. And this particular situation, if the part is not covered by intellectual properties, you can simply share it with support or ask us on the forum. We would be very happy to talk with you. What I would think that is the reason is that we have a non-closed geometry or non-closed volume, or lately I noticed that some very particular helical extrusions or helical cuts that are pretty long do not behave in a proper way. Let me just have a drawing. Okay, there's just an example. So let me grab a pen. Strange, I haven't done it so far. So first I'll just show you the logo. And let's imagine the situation that we create a helical cut for some kind of, and my mouse obviously has to go somewhere crazy. We make a helical cut, but for some reason, we decided to make a clip at this point so that the face that is being extruded is not continuous, it's being split. In this particular case, there might be problems with the geometry. Okay, erase the drawing. But at the same time, I highly suggest you share it with support, post a question on the forum. There's a lot of people who would be very happy to discuss this. All right, another question. Do we have the possibility of repairing the geometry? For example, gaps between the edges. At the moment, well, we at SimScale are focusing on the thing that we know best, that is simulations, and we leave CAD to great partners such as Onshape. So we do not provide automatic CAD repairs. At the same time, depending on the quality of the CAD or the size of the gap, it might happen that the mesher itself will completely ignore it. So you could consider this a part of the repair. Still, I highly encourage people to go and repair the CADs online, since it's just a click with a mouse. All right. If there, we've taken a little bit more time, I'm really happy that we are still here. If there are no more questions, I do not see any hands risen. I would like to thank you on behalf of the whole team and everybody who goes with to make this presentation and the work that prepares these tools. I hope that we'll have a chance of seeing each other next week when we'll be talking of a little different types of simulations and different improvements we can do using the advantage of online CAD designs and simulations. Thank you very much for your attendance. Just as a last note, this week we'll also upload the videos, and you will find a forum topic on SimScale and on Onshape with a post to the links and the simulations that I just discussed. All right, see you next week. Bye-bye.